Thank you everyone for joining the weekly talk series. So today we have two students, Shubhankar Gupta and Deepak Malia. So it's a pleasure to introduce Shubhankar. He's a PhD candidate in the Department of Aerospace Engineering at IISc in Bangalore, India. He works in the area. He works in the AI and Robotics lab, so AIRL for short, and focuses on distributed online learning, swarm robotics, multi-agent systems, decentralized optimization, and control theory. So he's supported by the 2024 KIAC PhD fellowship. His work has appeared in venues like the Transactions on Machine Learning Research, so TMLR, that's what he's probably presenting today, and in the AAAI Conference on Artificial Intelligence. So he received his BTech in Mechanical Engineering from IIT Kanpur and an MS in Aero and Astro from Purdue University in West Lafayette in the United States. He's previously worked as a project assistant at the National Aerospace Labs and at the Aeronautical Development Agency, both in Bangalore. So Shubhankar, pleasure to have you. Thanks for agreeing to give this talk. So over to you.
Thank you for such a kind introduction, and thank you for inviting me. So I'll begin the talk. So today's talk would be about one of our recently published works titled DOME, Distributed Online Learning Based Multi-Estimate Fusion for Cooperative Predictive Target Tracking using a Robotic Swarm. So let's begin. Yeah. So the motivation. So as we are seeing in the current era, as the robotics technology is getting more economical, miniaturized, and more reliable, so we have seen increased interest in the area of swarm robotics, particularly its applications regarding search and rescue, precision drug delivery, surveillance, etc. So in all such applications, one of the key challenges or key component is the cooperative target tracking. Essentially, in search and rescue, the robots could be tracking people. In precision drug delivery, the robots could be tracking a certain kind of cell, or in surveillance, the robots could be tracking vehicles or people. So in all this, our work in particular focuses on this key challenge of look-ahead trajectory prediction. So let's look at the scenario that we have considered. So there's a target that the swarm of robots have to track. These robots are communicating via some communication network, but the links, they can degrade over time or they can drop due to some adverse situation. On top of it, the robots may be having different kinds of sensors and prediction algorithms installed in them. So the question is, whose prediction would be more accurate at what time? So how do the robots, they figure that out in a decentralized manner? Because if they can figure that out, then they will be able to make a better prediction using shared information from their neighbors. So in order to enable this, we need some kind of decentralized collective intelligence. In particular, such a collective intelligence need to be able to fuse these individual predictions from different robots by using a decentralized adaptive fusion of shared predictions. So now the question is how to do that. So in this regard, in this work, we have looked into how distributed online learning architectures can help us induce such a collective intelligence. Let's properly define the cooperative predictive target tracking problem that we are dealing with in the paper, in the work that I'm talking about. So for this particular work, we assume that the robots, they all have a dedicated sensor suite as well as a dedicated prediction algorithm. So these sensors or prediction algorithms, SIAI, they can be different for different robots. And these robots are communicating based on some underlying, so based on some base graph like G bar. So they are like communicating, but this but the communication links between them, they can actually drop with the link drop probability of PLD. Therefore, making this network a random communication network. So there's one assumption that we have made here. It's that all the robots are able to observe the target at all times. So we'll talk about this assumption in the next slide, but yeah, let's keep this assumption in mind. So the current position of the target, it's available to all the robots. So the task for the robots is to actually predict what will happen after, let's say, 10 time steps, tau time steps. So each robot would observe the current target position via its sensor suite. It'll use its local prediction algorithm (AI) to give the prediction algorithms tau-step look-ahead prediction of the target's position. So in this work, we have assumed or we have modeled this prediction as consisting of two terms. So the first term is simply the true target position that will be after the tau time steps, and there's this uncertainty term which we are calling as the prediction drift, which is essentially the bias term that is affecting the predictions. So in this framework, we have assumed that the prediction drift can have any arbitrary unknown structure. It can be non-Gaussian or anything that we don't know. Yeah. So what happens is, so what we need to do, or like what is required is that each robot needs to use, each robot needs to use this its local tau-step look-ahead prediction to, along with the information or the predictions shared by its neighbors, to use some kind of decentralized multi-estimate fusion framework to output the final prediction that would be used by the control law in order to execute appropriate tracking maneuvers. In this paper or in this work, our focus is just this yellow block that you see, the decentralized multi-estimate fusion part. So that's what we would be focusing on, and the solution is also pertaining to this block only. Given that the link drops can happen randomly, and the prediction drift is arbitrary of any unknown structure. So now, as I had discussed in the previous slide, that we have made an assumption that all the robots in the swarm have access to the target's true current position. So that this can be seen as a limitation in practice, but still in real-world robotic operations, this assumption can be highly viable under two primary paradigms. So the first paradigm is the decentralized sensing and learning paradigm, where we can just have robots that are capable of independently monitoring the target, that utilize each robot, where in this paradigm, each robot would utilize a high-grade, long-range, wide FOV sensor. But this paradigm can turn out to be really costly. But we have this second paradigm as well, where we can have powerful centralized assets that monitor the target instead, such as AVAX, satellite, or radars. So they do a one-way So they do a one-way signal broadcast to the swarm. So this can be cost-effective and scalable. Note that this centralized sensing part is just to provide the ground truth to the swarm. The learning part of the swarm is still decentralized. So the second paradigm can be seen as a like a practical way to ensure that this assumption can be valid in real world as well. So now let's look into now let's look into some already existing multi-estimate methods that have been used in literature. So the first type of methods are covariance-based methods. So they usually require covariance information. But the issue is that due to some adverse situation, an increase in the bias in the predictions may not lead to an increase in the covariance of that prediction. So in such scenarios, such covariance-based methods, they can fail. Moreover, they require assumptions regarding consistency and correlation. Among these methods, the most robust method is the separate bias Kalman consensus fusion. Why? Because it directly handles the drift by modeling the drift as a random walk process. Still, because the drift can be of any arbitrary nature, using a certain model for estimating or predicting the drift may not work well in non-stationary environments. We also have this basic averaging method, which is the averaging consensus fusion, where you just have equal weights for the consensus fusion. Certainly, it won't require any covariance information, but the weights are equal, so there's no adaptation as such. Then we also have online learning methods. They also do not require covariance information. So for instance, we have distributed mirror descent. So it also uses equal weights in its consensus, but it has a prior online error correction mechanism that deals with the handling of the bias. There's greedy local as well. There's no consensus involved in greedy local, but it does a greedy selection of the most accurate prediction among the neighbors. So given these baselines, let's look into what the architecture, what the dome architecture is all about. So the dome fusion architecture, it consists of 4 phases. The first phase is the learning phase, where the target is where the target position is observed, and it is used to generate a loss function, which is then fed to a multiplicative exponential weights scheme to generate these hat weights, alpha hat weights and W hat weights. These hat weights that are being learned online, they actually undergo a periodic reset after every T0 discrete time steps. This T0 is actually a hyperparameter. Why this periodic reset is required is because in online learning or continual learning frameworks, you need to forget periodically if you want to eliminate biases. So in order to learn something new in non-stationary environments, you have to forget the old biases. So this periodic reset, this forgetting is required. So after the learning phase comes the local fusion phase, where these alpha hat weights are used to generate local trust weights. These local trust weights are then used to use the algorithm AI's prediction, as well as the robot's previous time final social prediction. So these alpha weights are used to generate the local prediction. This local prediction is then communicated in the communication phase, along with the W hat weights that they had learned in the learning phase. So once the relevant information is communicated, comes the social fusion phase, where this information that has been shared, essentially the local predictions and the W hat weights that have been shared, they are used to generate the social trust weights as well as the social prediction, which is the final prediction by the robot, by each robot. And this social prediction is then fed back to both the learning phase and the local fusion phase, which completes the loop. And so this serves as one iteration of the dome fusion algorithm. So as you can see, the dome fusion algorithm, it's quite it consists of analytic expressions. It's quite easy to implement, quite suitable for SWAM applications. And this is precisely what allowed us to do a theoretical convergence analysis as well, which makes this kind of online learning interpretable online learning. So in order to prove theoretical convergence, we had to make certain assumptions. So the first assumption was regarding unique asymptotic optimal configuration. So what it says is that the neighborhood performance configuration in terms of the prediction loss gets fixed at t tends to infinity. What it means is that for the ith robot, there exists a unique robot which can be either itself or its neighbor that incurs the least cumulative loss out of all the robots in the local neighborhood as t tends to infinity. So we made this assumption, and then we also made another assumption, which was regarding cumulative loss, regarding the cumulative loss difference growing at least sublinearly with time. So what it says is that the cumulative loss difference between the other robots and the best performing robot grows at least sublinearly with time. This in practice holds when the best robot remains fixed for finite duration or may change intermittently. So given these two assumptions, we were able to show theoretically that the expected values of the social fusion weights, they converge over time. So in particular, for the inaccurate predictors, the expected social fusion weights, they converge to 0, whereas for the accurate predictors, the social fusion weights, they converge to a finite value, which is dependent on the communication link drop probability. We can do a similar analysis for local fusion weights as well, which is actually which can be considered as a subset of the analysis done for social fusion weights. But without the loss of generality, we just showed the analysis for social fusion weights. Now let's come to performance evaluation. So we carried out a numerical simulation in MATLAB to check its performance. So we considered a horizon of 1400 discrete time steps with a sampling period of 0.1 seconds. We considered a look-ahead window of 10 time steps. So the robots have to essentially get accurate predictions of where the target will be after 10 time steps, which is 1 second here, given the sampling period. So the loss function was designed as shown, and we considered for the first study, we considered a number of robots to be 6. So to simulate an adverse situation, we considered the base graph to be the worst case base graph, which is among the undirected connected linear topologies, which is the linear graph. So this is the base graph, and in this base graph, the links can drop with the probability of 0.1. So this is the graph for communication. And the drift model, essentially, it has a bias term, and it also has a zero mean Gaussian noise. So for the bias term, we modeled the bias term as a stochastic switching bias model. So here, with some probability, it can switch to a growing bias state or a receding bias state. So in the growing bias state, the bias will keep on increasing until a limit is reached, and in the receding bias, it will go to 0 eventually. So given the simulation setup, and note that the switching bias is quite stochastic in nature. It's certainly not Gaussian, and also please make note that DOME did not know the model of the drift that is being simulated. So for the DOME algorithm, the drift model was unknown. So given such an adverse situation where large biases can happen, and further at certain times in the simulation, robots are randomly assigned a large bias value or a small bias value, such that at least half of the population out of the total number of robots would have inaccurate predictions. So yeah, so given all this, so this is what we got for 500 simulation runs for each method. So we did a Monte Carlo, and what we saw was that DOME performed quite nicely. So we had a 74% loss reduction relative to the next best method, which is the separate bias Kalman consensus fusion. It demonstrates quite low variance as well, as you can see. And it's model, again, as I had said, the DOME is like model agnostic online learning. It doesn't involve any model regarding the bias or the drift. On the other hand, SBKCF, it actually assumes that the bias follows a random walk process, due to which it showed limited robustness under non-stationary environments where you have unknown or arbitrary drift dynamics. Okay, now let's quickly look at the MATLAB simulation video as well. So as you can see in the bottom middle plot, what it shows is that it essentially shows at what time which robot's prediction algorithm is undergoing a large bias. So as you can see, the environment is non-stationary, and also look at the bottom right plot or graph. It shows how the communication links are dropping, and which nodes are getting black. So a node getting black means it's entering a growing bias state. So as you can see, things are quite non-stationary. And the upper right plot shows the performance gap between the baselines and the proposed algorithm, and it shows that it performs quite well. Yeah. So we also carried out certain other studies. So we carried out a scalability study, where also DOME showed approximately 72% loss reduction relative to separate bias Kalman consensus fusion. And we can also see that beyond n equals to 10 number of robots, the average cumulative prediction loss curve sort of flattens. So it shows that the DOME algorithm is decentralized and quite scalable. So increasing the number of robots won't degrade the performance. We also did an ablation study. So note that DOME involved a fusion layer, and within each fusion layer there's an adaptation because of the weights. So we from the ablation study, we saw that when it just comes to having a fusion layer, having a social fusion layer is more important than having a local fusion layer. Whereas when it comes to adaptation inside the fusion layers, the local adaptation is more important than the social adaptation. And the periodic reset, the forgetting part, is actually quite critical for online learning paradigms, especially for non-stationary environments. We also checked the DOME under network degradation. So we increased the probability of link drop probability from
Shubhankar,
0.01
just if you can finish in next 2 to 3 minutes. Yeah.
Yes, I'll be very quick.
Okay.
Yes. Yeah. So as we increase the link drop probability, we see that at 50% link drop, even at 50% link drop probability, the prediction loss is below the 100 median, which is actually well below the best baseline method that we had compared with. So yeah. So just to check that the effect of noisy observations, because we had assumed that the robots have access to the true current target position. But what if in the second paradigm, the centralized sensing and decentralized learning, the satellite or the radar is sending them a noisy observation? So what happens in such a scenario? So we considered such a scenario for this MATLAB study, and we can see that as we increase the magnitude of the noise from 0 to 1 meters, the increase was only 5.8%, whereas if you increase the noise from 0 to 10 meters, the prediction loss increased by 80%. However, it still was within acceptable prediction loss. It was still below 100 median value, which is again well below the best performing baseline for the zero. I mean, for the zero variance case. I mean, the zero noise case. So yeah, so here also, like we see that it's, I mean, it's quite it can be quite compatible with centralized radar or satellite broadcasts. We also, just to check, if it works in ROS Gazebo as well, we validated the framework in ROS Gazebo simulation as well. So we considered different robots, and 1 second. So for each robot, the prediction algorithm that we installed in the, or like we gave to the robot, was essentially a polynomial approximator with different degrees of polynomial. So, and we were actually able to see that, yeah, based on how the target is behaving, for example, when the target was moving in straight lines, the robots that had the lower order polynomials, they were more given more weightage compared to the robots having a higher degree polynomial. So yeah, so that is what we saw in the ROS Gazebo implementation as well. Yeah, and yeah. So in conclusion, so we have a distributed online learning multi-estimate fusion framework, which involves a weighted fusion of local social predictions. It involves a decentralized loss-driven online learning. It handles unknown arbitrarily structured prediction bias and communication link drops. So we showed that the conditional expectations of the fusion weights converge. And numerical simulations also showed that DOME outperforms baselines, achieving approximately 74% lower prediction loss. DOME is scalable, resilient to network degradation and noisy observations. Further, the underlying mathematics of DOME can generalize to many decentralized privacy-preserving prediction tasks that are found in, for example, finance, where you can have multiple trading bots cooperating to generate predictions. We can have we can use it for weather forecasting as well. We can use it for predictive diagnostics in healthcare or smart grids and supply chains as well. So that's all for my talk. Thank you.
Thank you, Shubhankar. It was a very nice talk. So now the floor is open for the questions. If anybody has questions, they can ask directly or they can type in the chat box so that we can read it out for them.
Shubhankar, I have a question on scalability.
Yes, yes.
Did you do tests on scalability of this approach? Like how did you do the tests?
Yeah. So
I think you had one of the results which I kind of missed.
Yeah. So essentially, what we did was that we assumed a similar. So the underlying base graph was still linear. So we started with 2 robots. So again, we had this thing that half of the population at least will undergo failure, and that is randomly chosen at different time steps.
Okay.
So considering, so we still, for the scalability test also, we still considered the adverse conditions that we were simulating for the main simulation, and then we just kept on adding new robots.
But for the same graph, right? Or same size of the graph, or?
No. For the same type of the graph, which is the linear network.
Type of the graph, okay.
Yeah, because it.
But then you also increase the size of the, like.
Yes.
Size of your domain along with the number of robots that you added.
Yeah. So what do you mean by the size of the domain? I'm sorry.
No, here, like what is the range of the, like what is the size of the graph, like, or what they're exploring for?
Oh, so essentially each node on the graph is essentially would represent a robot. So let me.
Okay.
Yeah.
Sure.
So each node on the graph would actually represent a robot. And so this communication link essentially tells, okay, if I'm getting information from my neighboring robot or not. But the links can again drop. As I said, we have a communication.
But your graph is changing over time, right?
Yeah, the graph is changing. It's a random communication graph.
Yeah. So now, like, if did you see any behavioral change when they kind of created multiple clusters, or like they created clusters and started doing tracking separately?
Yeah. So yeah. So certainly, because it's a very worst case linear connected topology. Because why I'm calling it worst case is because these guys have just only 2 neighbors, and the The guys on the edge, they have only one neighbor. If they get disconnected, then they only have got to rely on their own prediction. If they are faulty, they are going to undergo like huge penalty for being faulty. So yeah, we did see all that. Actually, even when even in the MATLAB simulation video, you can see that when such things happen, you see some changes in the slope. But on top of all those changes, DOME is performing like quite well compared to that. Why that is happening is because DOME, again, the DOME framework, it works in two phases, right? So in the local fusion phase, in the local fusion phase, what we are doing is that we adaptively fuse my current algorithm's prediction, but my previous time final social prediction as well. So because I'm also yeah. So I can, if my current prediction is bad, even if I drop, if my communication link gets dropped, I can still rely on my previous time step look ahead prediction, which may not be that bad.
But here you're not adding any constraint on like you need to be connected to others in the network. Like if I kind of force that constraint that you always need to be connected.
Actually, yeah. So this work focuses purely from the estimation side. It's not from the control side. So yeah.
Okay.
So that's the controls part.
Yeah, that's what I was going to to know. Like now, based on the information, can I also decide like where should I go next?
Yes.
Or like that. Yeah. Okay.
So
and also,
based on who has the best information, you can change your leaders. You can actually connect with the guy with the better. So it's a dynamic leadership thing as well, like because the leader will change dynamically.
Yeah. Sure. I think Sujit had a question.
I have a question. So what will happen when you disconnect and you connect it again back? So are you guaranteeing that there won't be any disconnection in the network at all? Because information, one side has it and the other side doesn't have it. Right?
So disconnections can totally happen based on the random graph that we have assumed for the framework. So, and that is what is being reflected in the analytical, the theoretical analysis as well. So if the probability, based on the probability, link drop probability, things can go bad as well.
And to what extent a disconnection is okay, or not getting an observability is okay? Before we can again restart.
I didn't get the question.
So till what extent you don't get any information?
So even if the communication link drop probability is 0.5, we see nice performance. So as you can see here, the number 4 here, it represents PLD equals to 0.5. So we see below 100 of cumulative prediction loss performance, which is good because it's better than even the the topmost baseline.
Okay. Good.
Yeah, just one last question if you are running out of time. So you are not using any covariance tools to decide on for which sensor you have to give more weightage, right?
No.
The sensors that you considered in the simulations, are they heterogeneous or homogeneous types?
So yeah, so we have abstracted them to be heterogeneous. So they can be anything essentially.
Okay.
So we have abstracted them as SI and AI, right? And that AI I showed you, right? How the prediction from each AI, which is basically the prediction algorithm, is modeled.
Okay.
So the prediction from each algorithm is modeled as an arbitrary unknown drift, which can have any arbitrary structure. So this is actually a standard assumption in online learning literature.
Okay. So okay, that's why you don't need to care about the covariance because
yes.
Okay, got it.
Yes.
Okay, I think we need to land the plane there and stop. Let's thank Shubhankar once again. Thanks, Shubhankar, for a great talk.
Thank you.